Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the course on computer aided drug design. We will talk more on concept of molecular mechanics and force field. In the previous class I introduced these concepts to you. There are two different major computational methods for calculating structures, the 3-dimensional structures as well as some properties. Okay. One is called the quantum mechanics approach. So in the quantum mechanics, the nucleus and electrons of the molecules are separately constituted. That means you look at electrons separately, nucleus separately. There are two approaches here. One is called the ab initio method here, the other one is called the semi empirical method. Okay, the ab initio method is very rigorous. It requires a lot of calculations. There are no stored parameters. It takes a long time. It can be used only for small molecules. Okay, tens of atoms. The other one is the semi empirical method. It is faster, so a lot of parameterization has been done. So it calculates certain features using some regression relationship. It is less accurate. It can be used for large molecules also, that means hundreds of atoms. Okay. These quantum mechanics can be used if you want to calculate molecular orbital energies, if you want to calculate partial charges, if you want to calculate electrostatic potentials, dipole moments, you want to calculate what is the energy required for breaking bonds, energy required for forming bonds, and so on actually. The other method is called the molecular mechanics method. Okay. Here this is a simpler version of quantum mechanics. Here you do not differentiate between the nucleus and the electrons. Okay, so it is lumped together as atom like particles. Okay, it is like balls. Then these balls are connected by springs. Okay, they are all connected by springs. So you use classical potentials like Hooke's law for calculating energy. Okay, so we can calculate a structure, dynamics, and total energy, entropy, free energy, and diffusion. So we can go up to thousands of atoms in molecules. So if you are doing a docking of various ligands to a protein, then we always use this molecular mechanics method. Okay, so it is widely used for docking calculations, it is widely used for molecular dynamic studies. So most of computer aided drug design uses molecular mechanics, and little bit of semi empirical method also is used for calculating partial charges, electrostatic potentials, and so on actually. Okay. So we will go more into the molecular mechanics initially. So the energy is made up of 4 different components: the stretching energy, okay, stretching energy, then the bending energy, the torsion energy, the non-bonded interaction. Okay. So the stretching, if you look at a particular molecule, assume it has got 4 atoms connected or 4 balls connected in 3 bond formation. Okay. So this is called the bond stretching. Okay, 2 atoms are stretched, or conversely maybe pushed in or compressed, that is called the bond stretching. Then we have the angle bending. Suppose you have 3 atoms, okay, then the 2 bonds can bend inwards or outwards. The third is the torsion energy. Okay, this is like a twist in the 3rd dimension, that is the torsion energy. The 4th one is called the non-bonded interactions. That means look at these 2 atoms, they are not connected, but there could be some interaction between these 2 because of electrostatic forces, van der Waals forces, or even hydrogen bond formation if the atoms are favorable. So they are called non-bonded interaction. So you have energy terms for each one of them, you add up and then you get the total energy of this particular molecule. Now let us look at each one of them independently. Stretching energy, E is equal to summation of Kb r minus r naught whole square. So, r is the distance here between these two atoms, r naught could be the equilibrium, r minus r naught is the distance you have stretched or how much it has been elongated or even compressed. So, Hooke's law, as you know, it is delta x square, so that is why you have a square term coming in. So, Kb is a constant, you are doing summation because there could be many bonds, so there could be many stretching happening. So, that all adds up to this energy. So, we have parameters Kb, we have r naught, we need to know them. So, depending upon the type of atom, this one and this one, the r naught will change, Kb will change, okay. It could be carbon carbon, carbon nitrogen, carbon oxygen and so on, and between carbon carbon also there could be a single bond sp3, double bond sp2 or triple bond sp or aromatic and so on actually. So, you need to have that data for the Kb as well as for r naught for various systems which is stored, okay. They are called parameters. So, we need lot of parameters. So, depending upon the type of softwares, the number of parameters may vary and you may have large number of parameters in some softwares, and some softwares may have less number. So, between softwares you will always get a difference in the energy calculation, okay. So, if you look at the graph, because it is r minus r naught square, it will appear like a parabola. So, you stretch, the energy will increase, you pull them together or push them together, energy will increase. So, this is the optimum, okay, optimum distance, okay. So, if you push them inwards, energy will increase, if you pull them out, energy will increase. Of course, you can't pull beyond certain distance, as you know, the bond can break, bond is stretched towards the point of dissociation, okay. So, this is the optimum, and ideally you would like to have that sort of optimum value, okay. Now, let us go to bond stretch. Again generally we use a quadratic term as I showed you, but the energy can be very large for very elongated bonds. For example, as you can see here, the energy goes up like a parabola. So, the energy numbers go up even if there is a small change in the r minus r naught. So, quadratic has that problem, okay, especially for elongated bonds. There is something called Morse potential which is more accurate. The term for that is like this: E stretching is equal to summation of dE 1 minus exponent minus beta r minus r naught whole square, okay. Okay, so, now this has got 3 different parameters or constants, but this is more accurate than this, especially for elongated bonds, because the energy values will look very high, because this is a quadratic term. So, many softwares try to use this rather than use this. Cubic is not used because it gives you a wrong asymptotic form, but sometimes quartic is also used, that is r minus r naught power 4, okay. So, you may have r minus r naught square, r minus r naught cube, r minus r naught power 4. So, you have many constants coming here. So, if you look here, a quadratic you will have only 2 constants. If you go to a quartic, you are going to have 1, 2, 3, 4 constants, okay. It also fits very well. Morse potential, if you go, that is also quite accurate. Here you have 3 constants, okay. So, you have to note that r naught is not the same as the equilibrium bond length because of non-bonded contribution, because there could be attractions because of electrostatic when you consider a molecule with many atoms. So, r naught will not be the same as the r naught when we have just a C type of bond or CO type of bond, but once you add many other atoms, the r naught changes because of the other interactions that is happening, okay. So, if you look at it, okay, this is the quadratic, okay, this is the 4 quartic, and this is the Morse, and this is the actual exact. So, as you can see, many a times Morse fits much better than a quadratic or a quartic. Let us go to bending energy now. Bending energy, you have 3 atoms and there are 2 bonds. So, the angle could be less or it could be extended or expanding or compressing. Again you go for a quadratic form like this, E is equal to summation of k theta theta minus theta naught square. So, you have two parameters theta naught and k theta, and again you do a summation because there could be many bonds where there could be a bending happening. Okay, now again you are going to have a parabolic type of relation. So, if you expand the bond, again it may be going up energy, if you make it acute, again the energy may be going out. So, obtuse, acute, both times energy will be going up in a parabolic form. This is the optimum. You could also change the k, so you may have a shallow looking quadratic term like this or like this. Okay. So, you can have different types of quadratic. Larger the value of k, the more energy is required to deform an angle from its equilibrium, okay, because the energy becomes very high, whereas this type of shallow looking things you do not need very high energy to deform from its theta naught. Angle bend term, again you can have a this is the quadratic form, okay. You can have even go for quartic form, cyclopropane like, as you know cyclopropane is like this, right. It is a cyclic, you have here CH2 CH2 CH2, it is a very strained system. So, you may have to go for this. Special atom types may be used for very strained atoms. This is a very strained system, remember that. Okay. Then we go to torsion. Torsion, the expression for the energy looks slightly different. So, you have a torsion is a twist, as we can say, it is a twist in the third dimension. So, we have terms like A 1 plus cos n tau minus phi. So, we have constants, these are the parameters we will call it, okay. These are the parameters which these are the parameters which need to be stored in your database. So, torsion energy, for example, if you take a butane like system, okay, this is a cis butane like, so the energy is going to be very high. If this is a trans butane, energy is going to be lower, as we might have studied, okay. In between various configurations of these four, you may have different energies, okay. So, as the tau increases you see this cyclic, but the energy numbers is very high for a cis, energy value is very low for a trans configuration. So, you can have different forms of the equation. So, we can have a single cosine with the appropriate barrier multiplicity, that is Vi and n, or we can even go for these type of relation, cos theta minus theta naught, cos 2 theta minus theta naught, cos 3 theta minus theta naught. So, if you have a dipole type, you can put one fold, two fold, conjugation, three fold, steric contributions and so on actually, okay. So, we can go down to 3 terms here, or we can stick to one also. This is called the torsion energy. Now, we can also have cross term. Imagine that just because you are stretching a particular bond, the other bonds and other angles remains constant. That is not true. There is always going to be some interaction. If I bend a system, of course the bond length may change. So, that is why we have call it cross terms. For example, you can, when I stretch 2 atoms, this stretch maybe get disturbed. For example, if I stretch, maybe this bend will get disturbed. So, there could be an interaction between stretch and bend, okay. If I bend one angle, I am sure another angle may get disturbed. So, there could be an interaction between bend and so on. So, you could have similarly, when I stretch, maybe the torsion gets disturbed, when I bend also torsion get disturbed. So, there is always a interaction, and the energy, the terms are not just independent of each other. So, some softwares consider cross terms, interaction terms between stretch, bend and torsion. For example, stretch Ri minus Ri naught, Rj minus Rj naught, stretch bend. So, you see that the terms come in here multiplying each other, bend. You can have bend torsion, you can even have a 3 term coming into the picture, okay. So, some softwares consider the cross term depending upon the complexity you want to put in, realistic factors you want to put in, you can have more terms, and of course more the terms I need to have more parameters known. For example, this is a new parameter Kij, which talks about the interaction between 2 different stretches I and j. So, I need to know that parameter value. In addition, computational time also will go up because you have extra terms into your energy calculations. Okay. So, the out of plane bending, imagine you have a molecule with 4 atoms, okay, 3 are on the plane and 1 is up. So, that is called out of plane bending term. Angle to plane or distance to plane can be used for the out of plane bending. So, angle or distance, that is called improper torsions for out of plane bending. Chirality constraints are required in united atom force field. Okay. So, we can bring in those aspects also, out of plane bending, energy related to that. So, that could be based on either distance or that could be based on the angle. Then we have non-bonded interactions, and the important ones, van der Waals and electrostatic. Okay, what is electrostatic? Imagine there is a charge on this atom Qi, there is a charge on this atom Qj, Qi Qj by distance Rij, that is the electrostatic term. Okay. And van der Waals term looks like this: Aij Rij raised to the power 6 plus Bij Rij raised to the power 12. Okay. This is called the van der Waals term. So, here the denominator is Rij, whereas here you have 2 denominators, Rij 6, Rij raised to the power 12. Okay. So, this is the van der Waals. Okay. So, this contributes negatively, this contributes positively towards the energy term. A and B are constant. Okay. And there are variations to this, we will look at some of them. Okay. So, we have the repulsion, we have the attraction, here the electrostatic interaction, these are non-bonded, and there are many non-bonded interactions like hydrogen bond, dipole, and so on. We will look at some of them later. Okay. So, how will the van der Waals look like? So, if they are far away, there is going to be attraction, if they come very, very close, there is going to be repulsion. Okay. That is why you have these 2 terms. Okay. Far away, 2 atoms, there is going to be attraction, and when they are closer, there is going to be repulsion. So, the A is called the degree of stickiness of, and B is called the degree of hardness. Okay. B is called the degree of hardness, A is called the degree of stickiness. Okay. You can modify by changing this term. We can have Qi Qj divided by d Rij. Okay. D is the dielectric constant. So, the D changes depending upon R. Okay. So, we bring in this extra term in the denominator for the electrostatics. Normally, if we ignore that, it will be Qi Qj divided by Rij, but we bring in distance dependent dielectric constant here. So, that means when they come closer, you may have different dielectric constant, when they are far away, you can have different dielectric constant. Okay. So, what happens? There are partial charges are created due to the asymmetric distribution of electrons in the chemical bonds, right. So, if you have there are electronegative atoms and electropositive atoms. So, there is always going to be some partial charges created. Okay. O means you may have negative slightly, they are all delta negative and so on. So, that is called Mulliken charge. Okay. Polar covalent bond like HCl, the shared electron oscillates between the bonded atoms, whereas chemical bonds between atoms within a molecule consists of 1 or more electron pairs distributed among the connected atoms. And bonding electrons are not equally distributed among the atoms that have different electronegativity. Like I said, O minus you may have, N, okay, maybe carbon may be different, positive. So, a small charge which leads to all these electrostatic forces. Okay. Now, let us look at benzene for example. Okay. If you look at benzene, so we have carbon. So, the H being positive, you have a small delta positive charge. So, the carbon has to take in a small negative charge because the whole molecule per se is neutral. So, these carbons will have slightly negative charge. Of course, in some cases carbons can have positive also, we look at it. Look at this, okay. Benzoic acid, we have a C double bond O, OH, as you know H, so it has got a positive charge, okay. This O you can see has got a negative charge, and this O has got a negative charge. This O has a higher negative charge than this O, you see this. Carbon has a positive charge here, whereas in the benzene you see carbons had negative charge. okay. But then this carbon has a positive charge, but all the carbons in the aromatic have negative charge, you can see, and they are not same, they are all very different because of this benzoic acid, okay. They are symmetric here, but this COOH is closer, so these carbon have very low negative charge, okay, whereas these carbons have higher negative charge. So it is different because of this particular COOH group here, okay. Look at this NH2, okay. Okay. So we have a benzene connected with the NH2 here. So nitrogen minus 0.156, and again all these carbons on the benzene ring, and again as you can see it is not same, unlike here because of the NH2 group, okay. These carbons have different charges. So these two carbons have same negative charge, this carbon has lesser negative charge and this carbon has higher negative charge, okay. Between this and this, if you see benzoic acid and aniline, the carbon here are quite different as far as the charges are concerned, okay. You can see a lot of difference. That is why the reactivity changes, that is why the electrostatic values change, and so on actually. Okay, there are softwares, for example this particular software, it can calculate the charge distribution if I put in a molecule, okay. We will look at it at some point, but this particular software called Chemaxon, it can give you the charge distribution here, okay. Hydrogen bond, that is a very important term, because many ligand protein interactions are based on hydrogen bond. They have a different form of equation, okay. If you look at van der Waal, we had r power 6 and r power 12, okay. Here you see r power 12 and r power 10, okay, a Rij 12. What is this hydrogen bond? So this oxygen here becomes a hydrogen bond acceptor, okay. This hydrogen here, it is a hydrogen bond donor here, okay. So you can have all the three may be involved, okay. These two may be hydrogen bond donors, this may be hydrogen bond acceptors, and you can have a very network of hydrogen bond formation in water molecule, okay. So they have a different terms, as you can see with respect to van der Waal. So non-bonded interactions can be made up of van der Waal, electrostatic and hydrogen bonding. Van der Waal, electrostatic and hydrogen bonding. The repulsive part of van der Waal potential due to overlap of electron distribution is called Pauli's exclusion principle. It rises very steeply because of steric repulsion, okay. Attractive part of van der Waals potential due to London or dispersion forces, it is dipole induced dipole interaction, it is proportional to r power 6, okay. It is proportional to r power 6, as I showed you here, proportional to r power 6, okay. That is called the London or dispersion forces, okay. So different types of forms for non-bonded interaction, this is called the Lennard-Jones potential. We have a summation of 4 epsilon sigma Ri j raised to the power 12 minus sigma Ri j raised to the power 6. So r minus 12 rises too rapidly, it is easy to compute. We have another one called Buckingham potential, a exponent minus b Rij minus c Rij minus 6, but it is slightly harder to compute, you have to calculate this. Or we can tabulate sigma and epsilon for each atom, obtain mixed terms as arithmetic and geometric means like this, okay. Sigma is equal to sigma plus sigma AABB by 2. So sigma AB could be geometric means, or it can be even arithmetic means for sigma and geometric means for epsilon, okay. So different approaches by which we can calculate these terms for AB or IJ. So when you have a drug and it is going and binding to a receptor, that is your protein, there are a lot of bonded interactions, non-bonded interactions. For example, your covalent bond is bonded, there is a strong bond, you can look at the energies 40 to 110 kilocals per mole. whereas ionic or electrostatic interaction, these are all non-bonded, it is only 5 to 10 minus 5 to minus 10 kilocals per mole, ion dipole or dipole minus 1 to minus 7, hydrogen bond minus 3 to minus 5 kilocals per mole. So you see that they are all quite small when compared to the bonded, all these non-bonded interaction or energies are very small when compared to this, but in ligand protein binding only these play a very important role, because there is no bond formed, there are only non-bonded interactions, electrostatic, van der Waals, pi and charge, salt bridge and so on actually. If you look at the effect of distance, as you know, electrostatic we have Qj divided by Rij, so it is proportional to 1 by R, okay, whereas if you look at charge dipole type of interaction, it is related to 1 by R square, okay, dipole it is related to 1 by R raised power 3, dipole quadrupole 1 divided by R power 4, charge induced dipole 1 divided by R power 4, dipole induced dipole 1 divided by R power 6. So we call this as the long term interaction, because all these other terms will rapidly decrease as the distance increases, whereas this decreases only linearly, whereas this may be decreasing, all these decrease non-linearly, quadratically, raised to the power 4, raised to the power 6 decrease. So they decrease very rapidly, whereas this decreases only linearly, so we call these as the long term interaction. So in the long distance, when the ligand and protein are there, initially we start having only electrostatic forces, but as they come closer and closer, all other forces start taking place and they become important in judging how the ligand binds into the active site, what type of conformation it takes and so on actually. Okay. So we will continue more. There are many parameters we saw, right, so many different parameters, constants, k values in the multiplication, r naught, theta naught, so many parameters, okay. So all these force field or molecular mechanics softwares need to have a database of parameters. So where do they get them from? They get from literature, experimental data, sometimes they do very exact calculations, that is called ab initio calculations. So much of the data is from small molecules. So I collect data from small molecules, but when I go to a larger molecule I assume those parameters do not change, you understand. So if I have a small molecule which has got a CO bond, I get the parameters for that, but when I go to a large molecule and it has a CO bond, I assume that parameters do not change. That is a very important assumption I make, okay. So parameters for fragments of proteins are appropriate for that fragment in different contexts also, okay, in different contexts also, that is a very important point we need to. So whether it is in a small molecule or in a large molecule, we assume the same parameters, that is a very important parameter approximation. So much of the data is from small molecules, okay. We cannot get all these parameters from a big peptide, but using small molecules like 200, 250, 300 molecular weight, we get from crystal structure, because crystal structures, when you crystallize a organic molecule, we can get the length, angle, non-bonded coefficients, so we can run some molecular mechanics calculations and then fit the findings to the experimental data and get the parameters. We can get from vibrational spectroscopy, okay, some of the vibrational Raman or IR. We can also do ab initio quantum mechanics calculation. Calorimetric studies, we can find out heat of the formation, we can get delta G, okay, using some calorimeter. We can get from thermodynamic measurements we can get some. So all these experimental data can be used to get many of the parameters, and one important assumption is small molecule parameters obtained from small molecule can be extrapolated even if it is in a large, if it is a fragment in a large molecule also. Sometimes they are also got from ab initio quantum mechanics calculation. As I said, ab initio is a very accurate study, and you perform such very accurate experimental studies using very high end quantum mechanics ab initio calculations. Okay. So, this is how the parameters are got actually. There are many empirical force field, okay. Large number of force field softwares are there, okay. We will look at some of them and their form, but all of them will have basically the terms connected to bond stretching, bond angle, torsion, non-bonded interaction, and sometimes cross terms, okay. And some softwares will have lot of parameters, some softwares will have less parameters, some softwares are used predominantly for organic molecules, some can be used for inorganic, and so on actually, and some may even have metals, so parameters for metals, iron for example, zinc, copper, and so on actually. Okay. So, we will look at all these more in detail, how the parameters vary between softwares, how the equations look like between softwares, and so on actually. Okay. Thank you very much for your time.